In this video, I'm going to talk to you about periodic trends and periodicity. Now, periodicity is a term that refers to regular changes in elemental properties as you move across a period or down a group or family. As you can see, there are a number of periodic trends. And in this video, I'm going to specifically talk to you about atomic radius. Atomic radius is defined as the distance between two nuclei divided by 1/2. So it's the distance between two nuclei divided by 1/2. That is the radius. Now, this value is going to depend on the type of bond, whether you're dealing with covalent, metallic, or ionic. This value will change. I should also mention that this value is reported typically in very small units known as picometers, 1.0 times 10 to the negative 12th of a meter. So a very small value. And there are also different experimental methods that are used to determine atomic radii, and thus there are often small discrepancies among reported values. The atomic radius is actually a measurement of the the electron cloud. And after our discussions of quantum theory and the quantum mechanical model of the atom, this is no surprise. As you increase the number of shells or energy levels from principal quantum number 1 to 2 to 3, there is an increase in the size of the electron cloud, and thus there is an increase in the atomic radii. So that hopefully makes sense. I also want to talk to you about something known as the effective nuclear charge, which is designated with a Z subscript EFF for effective. This will provide a quantitative way for us to analyze the charge and to look at atomic radii from a mathematical perspective. So the effective nuclear charge is the net positive. I'm going to underline that. The net positive charge experienced by outer electrons. So we're talking about the outermost or valence electrons. And this number of effective charge is a way to quantify that. It is as the effective charge gets larger and larger, that attractive force, those electrons, as you know, are attracted to the protons in the nucleus. All right. This is a Coulombic attraction. And so as the charge or the attractive force goes up, the nuclear effective charge goes up, the atomic radius goes down. Effective nuclear charge is also determined by the number of protons. Okay, so how many protons are there? Are there 3 protons in lithium, or are there 10 protons in neon? The more protons that are in the nucleus, the greater that Coulombic attraction. In other words, the greater the overall effective charge will be, which means that those electrons will be pulled in closer to the nucleus. All right, now we're going to look at this mathematically, and I want you conceptually to look at this schematic diagram. So in the nucleus, you see the number Z. Now, I don't want you to confuse that with the effective nuclear charge. Z is actually the atomic number. In other words, how many protons are there? And the number of protons minus the number of shielding electrons. I'm going to go ahead and underline that as well. The number of shielding electrons equals the overall effective nuclear charge. Okay, so let's look at the schematic here. You see there's a couple different things going on here. There's an attractive force between the electron and the proton in the nucleus. But there's also repulsive forces going on among the electrons. So we have attractive forces going on between electrons and protons in the nucleus, and we have repulsive forces going on among the electrons. That's important to consider. Now, in this example, we're looking at phosphorus with 15 protons, and we're going to apply the use of this equation to calculate the overall effective nuclear charge. Remember, S is dealing with shielding electrons only. So what I want you to look at here is we have overall, we have a number of protons, 15, minus the shielding electrons. So we're not talking about outer valence. So we're not talking about any guys out here. Shielding electrons are these guys here. And if you count them up, there's a total of 2 in the innermost shell plus 8 in the second shell. So overall, we have a total of 10. So our ZFF in this case is going to be 15 minus 10, which equals the plus 5 that you see here. All right, that's where that number comes from. 15 minus 10 is plus 5. Again, where's the minus 10 coming from? Count the shielding electrons. There are a total of 10. Where does 15 come from? That's the atomic number or number of protons in the nucleus. The effects on the number of energy levels and the effective charge will change as you move either across the period or up or down a family or group. That is what periodicity means. That is a periodic trend that you will see. So as we move across from left to right, or as we move from top to bottom, we're going to see changes in atomic radii. I'm going to go through these changes with you. Now, here we have a graph. On the right side, we have a graph, and I want you to look at lithium. Then come on over to your periodic table, find lithium there. All right. As you move across, now take a look at beryllium. Each dot is going to correspond with a point on the graph. As you move from left to right, you see a trend, a periodic trend, where the atomic radius is decreasing, okay? All the way across to neon, this trend is apparent, all right? So radius is decreasing. I'm going to explain to you why. But first, the next trend, look at the right side of the periodic table. As you move down the right side, you can see we're increasing the number of shells, which means we are increasing the energy levels. So as you increase energy levels, you're increasing the distance from the nucleus to the outer valence electrons. Remember, it's the size of the electron cloud that defines the atomic radius. Each additional shell is that much further away from the nucleus. I want to talk to you now about the shielding effect that occurs from inner electrons. As you move down a group, for example, lithium down to francium, the atomic radius increases. The electron cloud gets larger. Not only do we have the fact that we're adding levels or shells, but there's also now additional shielding from the inner electrons. Each shell that is added is further away and has more shielding. Those inner electrons shield the charge or the attractive force. They minimize it. So there's yet another thing I want to talk to you about, and that is the electron repulsion that occurs among. Remember, electrons are repelled. They want to be as far away as possible. So all of these electrons in this area are also exhibiting repulsion among each other. All right, as you move across the period, the number of electron shells remains constant, right? So the principal quantum number is constant all the way across. Yet in this schematic, you can clearly see a trend. There's a periodic trend of decreasing atomic radius as you move from left to right across the periodic table. What's happening here is you're increasing the atomic number. In other words, more and more protons. Remember, protons are a major part of calculating the effective nuclear charge. They are the atomic number Z. Think about this mathematically. So if we look at this here, what we're basically saying is that this number is increasing as we move left to right, and this number is staying the same. Remember, it's the inner electrons that shield. We're not moving further out, so there's no additional shielding effect that's occurring as we move from left to right across the period. Yet we see the atomic radius decrease because we are adding protons, which means that that attractive force is greater, which means the electrons are being pulled in closer to the nucleus. Electron shielding is kept constant, so therefore the atomic radius will decrease. Now I want to talk to you about the effects that are seen for anions and cations. Recall at the beginning of this video, I said atomic radius or an ion's radius. Let's talk about this for a minute. Let's look at atomic number. Let's look at number 11 on the periodic table. Let's look at sodium. This is a Bohr model for sodium. Sodium in its neutral form. Everything I'm going to talk to you about is comparing the ion to its neutral form. So I'm comparing sodium in its neutral form to the sodium +1 cation. So what's going to happen here, as we've discussed multiple times, is sodium is going to give away this electron, all right? And what happens when sodium gives away this one valence electron here? This whole shell goes away. And we go from something that is this big to something that is this big. So cations have smaller radii because they have lost an electron. Now, if they lose all outer electrons like sodium did in this example, you go down a whole shell, as I just explained. If you lose one electron but keep that shell, you're still seeing a decrease in the electron-electron repulsion that I just spoke about. Let's now look at an example of an anion. Let's look at fluoride and compare it to its neutral form, fluorine. So fluorine is on the other side of the periodic table. So it, anthropomorphically speaking, wants one more electron. Recall the reason fluorine wants one more and sodium wants to lose one is to assume the most stable form, which is a full valence shell. We call that an octet. So fluorine accepts an electron, all right? So what does that mean when we compare fluoride to fluorine? That additional electron is going to increase electron-electron repulsion. And overall, that's going to increase the atomic radius. So cations have smaller atomic radii, anions have larger atomic radii when compared to their neutral forms. Now, let's take a look here and compare both cations and anions before we wrap this up. So let's look at sodium over here, since that was the example I did. Sodium over here. Now, in the red is the cation, the black is the anion, and these numbers are the atomic radii reported in picometers. Compare these values. 116 for the sodium cation versus 154 for its neutral form. Now let's talk about fluorine over here. Black being the neutral and blue being the ion. In this case here, compare the values. The anions are larger. 119 for the anion versus 71 for the neutral form. Again, the reasoning being, in the case of cations, they're decreasing electron-electron repulsion, decreasing the number of shells, and in the terms of an anion, those additional electrons are leading to an increased electron-electron repulsion. So in this video, I have begun to talk to you about periodic trends and the periodicity of the periodic table. I'll see you guys in class.